Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. Today I want to recap amorphous materials because in my experience that's a concept that most students find quite tricky. So if you're revising for an exam and you think there might be a question about what is an amorphous material or how might amorphous materials be used to make better medicines, get yourself a drink. I, as ever, can't get a drink because I'm in the laboratory and I've actually been banned by the chief technician from having a drink, so that's not good. But you can get a drink and let's get into it. Amorphous materials are very important in medicines because they have a number of unique properties. Because it's such a wide-ranging topic, there's a whole range of questions that might be asked in an exam. So I thought a good way of going about revision would be for me to write down some typical questions that I would set in a pharmacy exam, and we'll go through them one by one. So if that sounds good to you, let's make a start with question number 1. The first question is, what is an amorphous material and how does it differ from a crystalline material? If I were answering that question, I would start with some definitions. So, in a crystalline material, the molecules are arranged in a repeating pattern, and that pattern is defined by a unit cell. Since an amorphous material is the opposite of a crystalline material, we can write, in an amorphous material, there is no repeating pattern and the molecules are randomly distributed. If we think about a crystalline material, if we look at any molecule, and we look at how it's arranged with its neighbour, any two pairs of molecules will always be arranged in the same way. And so the bonds holding these molecules together will be the same throughout the whole crystal. When we apply energy to a crystalline material to raise it in temperature, we are providing energy to the system. Once the energy is high enough that it breaks the bonds holding these molecules together, all the molecules will fall apart at the same temperature. And so we see a crystalline material turn into a liquid or melt at a specific temperature, which we call the melting temperature. An amorphous material, on the other hand, doesn't work like that. If we look at any one particular molecule in an amorphous material, we never know how it's going to be arranged next to its nearest neighbour. There might be very little point of contact, a lot, who knows? What that means is then there'll be a range of energies holding molecules together in an amorphous material. So when we apply energy to an amorphous material to raise it in temperature, some of that bonding will break early on, other bonds which are stronger need a higher temperature before they break. And so we don't see an amorphous material melt. Rather, it turns from a solid into a liquid over a wide temperature range. So a key difference between an amorphous material and a crystalline one is that an amorphous material does not have a melting point. It does not have a melting point because it doesn't have a crystal lattice. So there's no crystalline lattice energy to overcome. Another consequence of that is that amorphous materials are going to dissolve faster because overcoming that crystal lattice energy is the main barrier to dissolution. So an amorphous material should be good for a pharmaceutical product because it's going to dissolve the quickest. And fast dissolution means higher bioavailability. And the last thing I would note is that an amorphous material is characterized by a glass transition temperature. Therefore, it seems to me super important that you can explain what a glass transition temperature is. And that's the point of the next question. With the aid of a diagram, explain how an amorphous material is formed. Include in your answer a description of the glass transition. In order to answer this question, you need this diagram. If I'm setting the exam, then I will either give you this diagram and ask you to talk your way through it, or I might say, explain with the aid of a diagram the formation of an amorphous material, in which case you've got to draw it. But either way, you've got to understand what the graph is showing you. So let's talk our way through it. On the y-axis, we have energy or volume, and on the x-axis, we have temperature. If we take a material at a high temperature above its melting point, it will be a liquid. Not a solution, mind you, just a pure liquid. In a liquid, all the molecules are randomly moving around at high speed. Therefore, material in its liquid state is going to have the highest energy and or the highest volume, which is why it appears at the top of the graph. As we cool the temperature down, the molecules are going to start to move around less, and as they move around less, they will start to come closer together. So the material is going to lose energy or volume, and we start to see the line come down on our graph. If we cool nice and slowly, when we get to a specific temperature, in this case the melting point, the molecules have time to come together and form a perfect crystalline structure, and we see a drop in energy and volume as the material crystallizes. On the other hand, if we cool a material really, really fast, we don't allow the molecules time to come together and crystallize. Remember that in a liquid, the molecules are moving around really fast, and in a crystalline structure, they're all aligned in a repeating pattern. So it takes a lot of time for the molecules to orient themselves properly into this crystalline structure. So if we cool down our liquid really, really fast, the molecules don't have time to come together and crystallize, and so they remain as a liquid. But that liquid is losing energy and losing volume. So we see our line carry on down like this. When we have a liquid below the temperature of one of its melting point temperatures, we say it's a supercooled liquid. And in principle, the supercooled liquid line is going to carry on to such a point that it crosses the line for our crystal structure. And that's a paradox. It's called the Kautzmann paradox, because it seems slightly paradoxical that a system where the molecules are randomly arranged is occupying a volume or energy lower than that of a crystalline structure. So nature intervenes to make sure that something happens, that the supercooled liquid can't occupy a volume or energy lower than a crystalline form. And what we see is a break or discontinuity in that graph. And that break is called the glass transition temperature. So you could define a glass transition temperature by simply saying it's a break or discontinuity in the supercooled liquid line that means the supercooled liquid doesn't occupy an energy or volume less than that of the perfect crystal. But we want a little bit more than that in our answer. So you've got to think to yourself, well, what's actually going on in my amorphous material at that point? You could look in the literature and try and find an answer, but you'll find lots of different answers because nobody really knows. So this is my take on what's going on, and since I'm marking your exam, if you're studying at UCL at least, it's a good idea to follow what I'm saying. If you're doing an exam somewhere else, follow what your tutor's saying. That always seems like a good idea. So my interpretation of that line is that above the glass transition temperature, the molecules are moving around. It's a supercooled liquid, but the molecules are reasonably able to move. What that means is, if we change temperature, doesn't matter whether we go up or down in temperature, the molecules instantly react to the change in temperature that we are making. And so the system is said to be in some sort of structural equilibrium. That is, the system is responding as we change the temperature. When we go below the glass transition temperature, on the other hand, as we change temperature, the molecules have kind of become frozen in place. I hesitate to use the word frozen because people think about water, and most amorphous materials, they have a glass transition temperature that's nothing like 0 degrees centigrade. But nonetheless, I'm going to use the word frozen because at least it will make you think about the molecules being kind of fixed in place. So as we change the temperature of a material below its glass transition temperature, the molecules don't necessarily have time to move in response, and the material is said to be brittle. Above the glass transition temperature, the material is said to be rubbery. If you want to see demonstration of a brittle material and a rubbery material, I put a video on YouTube where I smash a jelly baby that's been frozen in liquid nitrogen, and you can see the difference between a brittle and a rubbery solid. So really, when you're talking about how do amorphous materials form, the way I like to think about it is an amorphous material is effectively a liquid, but it's a supercooled liquid. Supercooled means it is at a temperature below the melting point of one of its crystalline forms, and that's kind of an unstable situation. And on that graph, as we cool it down, the energy and volume of our supercooled liquid is getting less and less and less. That means the material is becoming more and more viscous. And when we get to the glass transition temperature, the viscosity becomes so high that the molecules effectively become frozen in place. Right, that's how I would construct an answer explaining what an amorphous material is and how a glass transition works. Let's look at the next question. What processes could be used to make a material amorphous? Now, if you just watched the bit when we talked about formation of an amorphous material, hopefully you will see that amorphous materials form when we don't give the molecules time to crystallize. Therefore, any process which causes a rapid solidification of our material has the potential to make the material amorphous. It really comes down to how quickly can the molecules become crystalline or not. And if the process makes the material solid quicker than they can crystallize, they're going to be amorphous. That's the way I look at it. So typically, in the pharmaceutical world at least, there are 3 processes which we would use to make a material amorphous. They would be freeze drying, spray drying, or quench cooling. There are other processes that might make a material amorphous, okay, but this is a pharmacy topic paper, and so in the pharmaceutical world, those are the 3 most important processes. Freeze drying tends to make materials amorphous because you start with a solution which is rapidly frozen, and so the molecules get literally frozen in place, and the water is removed with sublimation. So we tend to get highly porous but amorphous materials. Spray drying, remember, atomizes a solution into small droplets into a cyclone of hot air, and so they rapidly evaporate, the water rapidly evaporates, and anything which is left behind which can't evaporate gets solidified into a particle. So we end up with highly spherical, small but amorphous particles. And the last one is quench cooling. So quench cooling literally means taking your material as a molten material and throwing it into something cold. We would typically use liquid nitrogen, which is minus 196 degrees centigrade. And again, the temperature of your material goes from whatever its melting temperature is, say 200 degrees centigrade, to minus 196 degrees centigrade in just a matter of seconds. And most things take hours to crystallize. So in this instance, you're going to get an amorphous material because it's gone almost 400 degrees centigrade lower in temperature in a matter of seconds. And we would typically use quench melting to make something amorphous if we didn't want to spray dry it or freeze dry it. You could, if you wanted to get really, really top marks, you could note that there are some other processes that you might use in the pharmaceutical world that may make a material amorphous, but it may not make a material 100% amorphous, but it certainly has the potential to make it a bit amorphous. And examples of that would be anything that's applying a force to a material. And the reason the force is important is because a crystalline material, remember, has all the molecules arranged in a repeating pattern. If we apply a force, we can knock those materials out of that alignment. And so you could note, for extra marks, a process like tableting or ball milling or air jet milling or something like that may have the potential to make a material partially amorphous. Right, let's look at the next question. What are solid amorphous dispersions and why can they help increase the bioavailability of poorly water-soluble drugs? Now, that sort of question is a formulation question. It essentially says, what is it about amorphous materials that make really good medicines? So it doesn't really matter how the question is constructed. It could, for instance, say, what are the benefits of amorphous materials in formulation? Or how does a fast melt tablet work? There's loads of ways that question can be written, but the answer is essentially the same. So I would start, again, with some definitions. And if the question specifically says solid amorphous dispersions, let's start there. The clue for a solid amorphous dispersion is in the name. Solid, amorphous, dispersion. So that means it's a solid material with the molecules randomly arranged because it's amorphous. And the dispersion means there's at least 2 things present. One of those things is the drug, and therefore there must be something else. And we would typically say that the something else is going to be a polymer. The polymer is used because a lot of polymers are water soluble, and because they have large molecular weights, a lot of polymers can't actually fully crystallize. They can be semi-crystalline, but that's getting a little bit complicated. But in the main, a polymer is going to be amorphous. So a solid amorphous dispersion is a drug dispersed in a polymer. Now, where I've seen students lose a lot of marks over the years is they don't define the different types of solid amorphous dispersion properly, and there are a few. In principle, the drug can be dispersed as molecules or particles. Now, I know I've said this before, but students typically use the word molecule and the word particle interchangeably, and they are not the same thing. Particles are macroscopic things that we can see with the human eye that contain trillions and trillions of molecules, whereas a molecule is an individual drug molecule. I can't think of a better word. The word is molecule. So you need to be very clear that molecules and particles are not the same thing. So in a solid amorphous dispersion, we can have molecules of drug dispersed in polymer, or we can have particles of drug dispersed in a polymer. And those are very different things. Molecules of drug dispersed in a polymer would be a solid solution. It's very similar to a solution, which would be drug dispersed in water, for instance. It's just that rather than water, we have a polymer. So we have a solid solution, which is two component, but one phase. Two components, drug and polymer, but one phase, because the drug is molecularly dispersed amongst the polymer. The other option is that the drug is dispersed in the polymer as particles, so discrete particles in the polymer phase, in which case we would say it's a solid suspension, exactly the same as a suspension of particles in water, but again, we don't disperse everything in water, we're dispersing it in a polymer. So in that instance, we have two components, but two phases. There's a polymer phase and a drug phase. And to get top marks, you need to note that the dispersion of drug particles, those particles could be amorphous or they could be crystalline. It's more likely that the drug particles are going to be amorphous, but if a drug is really high propensity to be crystalline, we can disperse crystalline particles in a polymer matrix. And the reason we get an improvement in dissolution rate is because the polymer itself dissolves very fast, and so we disperse particles in the stomach, for instance, and we get faster dissolution. So it's really important to say there are solid solutions and solid suspensions, and in a solid suspension, the drug particles could be amorphous or crystalline. So there are essentially three types of solid amorphous dispersion that you might want to describe. I know that there are hundreds of different types of solid amorphous dispersions, and it can get way more complicated than that. But really, for the basics of revision, just remember those three types. The next part is, why does an amorphous material in general lead to better bioavailability of a poorly water-soluble compound? And the answer that I would put is, the main barrier to dissolution for a crystalline material is overcoming the energy which is holding the molecules together in the crystal lattice, as I said earlier. Where you've got a drug which is particularly insoluble in water, it means it prefers its own company than that of water. So we've got to do something to break these bonds in order to get that drug substance into water. In an amorphous material, because there's no unit cell and there's no repeat pattern, the molecules are randomly oriented, there is no crystal lattice energy. There is clearly a small amount of energy holding these molecules together, but it's very weak relative to a crystalline material. So because there's no crystal lattice energy, the main barrier to dissolution is overcome. So generally we would find that the fastest we can get a solid form of any given material to dissolve is to make it amorphous. So right there, the main reason why amorphous materials improve bioavailability is that they remove the main barrier to dissolution. So dissolution becomes the fastest. You could, if you wanted to, for extra marks, go on to say, well, if I made a solid amorphous dispersion, for instance, I've got other effects going on. The drug itself might still be poorly soluble, but if I've dispersed it in a really water-soluble polymer, that polymer is going to dissolve really quickly. And so that kind of forces the drug into solution. And we only need it in solution for a small amount of time for it to be absorbed by the body. So I would construct an answer to that type of question in that way. Okay? I suppose the take-home message there is, read the question, look at what the question's asking you, and then answer exactly what the question asks. If it says specifically about solid amorphous dispersions, you need to talk about solid amorphous dispersions. If the question says, how does a fast melt tablet work, having a pre-prepared answer about solid amorphous dispersions isn't really helping. You need to say, well, a fast melt tablet is a freeze-dried tablet, so it's amorphous with a high surface area, and therefore it's going to dissolve quickly. Simple as that. Right, I think that's all we need to talk about. Those are the main types of questions that I would ask, at least, for amorphous materials. Hope that helped. If it did, would you please consider hitting the like button and subscribing if you haven't done so already, because it really helps the channel. Otherwise, good luck in your exams. Thank you so much for watching, and I'll see you again soon.